All right. Yeah, welcome everyone. Nice to be here again after 2 years, I think. I've not been traveling, and I think 6 years since the last workshop here. So good news, I will not talk for 30 minutes. I will talk for 45. No. So we had a workshop like this before, 2 years ago, actually, almost exactly 2 years ago at CFNS, Stony Brook. Was not talk workshop, so a little bit shorter, but we had a lot of people there. Back then, we wrote like a combined white paper proceedings, which we didn't publish. It's just an archive. So far, we have one citation actually from the yellow report because I wrote it in. We should really think about writing like proper proceedings which we publish somewhere. So that's a better citable and maybe get more. So I think what you do here is quite important. It's a nice overview over the field. So that's actually my comment on that. So we should do that. I think we can go with POS or something that's not too expensive, and we can find that money. If enough of you are interested in writing them, we should do that. So what do I worry about from a theoretical perspective, I say as an experimentalist? So the proton radius puzzle obviously is one thing which keeps me up at night. There was this difference back then between electron measurements and ionic measurements. The picture has changed a little bit, but it's still with us to some degree at least. And why do I do lepton proton scattering? Well, you say it's a point-like probe, right? There's no strong force, so it should be straightforward to calculate. And I think the people in this room are evidence that this is not as easy as it sounds, because there are all these extra terms which we have to figure out and control. And what I do is I measure cross sections and then I reconstruct the form factors, right? So to do that, we always have this picture, right? It's the Rosenbluth cross section for electron proton scattering, for example. We get these form factors in there, we calculate all of the other quantities, we get them out, and then we know something about the shape, right? How big is that proton? What's the distribution of charge and magnetization inside it? And we can do that even in like a bright frame with a Fourier transform, give like a spatial information about that. And that tells us a little bit how it's actually constructed. How do the quarks interact internally, right, to produce this, right? All of the mass is essentially quark-gluon interaction. Right? Forget about the Higgs. So it's important knowledge, but that's a very like simplified picture, right? That we get the radius as the slope of that, which is problematic enough. But then we have all of these guys. And when we say we do elastic scattering, it's actually a lie, right? There is no reaction where there's no photon produced. Actually, we always produce an infinite number of photons. Right? And it's kind of boggles my mind that we can calculate this as the series where we start with something which is completely off, and then add a term which is still completely off, and add more terms which are completely off, and end something which is very close to true. Right? And figuring out how to do this, right, is the tricky part. That's why we are here, at least some of us. How precise do we have to go? And just to motivate this a little bit, if you think about the proton radius, you might want to extract it in a completely model-independent way, right? That would be nice. If you don't have to fit a model, you only fit a linear term, because that's the radius, right? So if you can produce a data set where it's enough to fit the linear term, get that up. If you write down the cross-section, it looks like this, roughly, right? So it's 1 minus, some factor, of course, 1 minus some term q squared plus some other term q to the 4 plus higher orders. And it ends up that A is about 6 and B is about 30, right? So you want B over A times q squared to be small. Well, how small do you want to be? Well, let's say we want to measure the radius to 0.5%. So square root of A over 2 is within 0.5%. And we do that without knowing B, so B over A times q squared must be smaller than 2%. Right? I get a factor of 4, one for the over 2 and one for the square root. So if we solve this, Q squared needs to be smaller than 0.004. That's not unrealistically small. That's actually inside of the Mainz data set, and PRED is much below that. So that's not crazy. So you could fit that just with a linear term. But if you do that, you have to
put in 30 now. You have put in 30 there. For B.
Yes. Yeah. I mean, you have to know something. Yeah. I mean, that's the order of magnitude, right? Of course, if that is a much bigger, then you have a bigger problem. But that's what we think it is. Right? So, but even if you check that, we need to measure A to 2%, right? But the effect on the cross section is only 1 minus A times Q squared. You add a small Q squared. So, but you measure cross sections, right? You measure that one, and all your error scale is that one. So you have to measure the absolute cross section or the change in the cross section to 0.048%. So half a per mil.
General question.
Yeah.
Is sign of known or even sign unknown?
Well, it's not known from a priori, but from the measurements, right? If you do the fits, we know B is in that order and A is in that order, right? These are rough numbers.
From fits, it's
like
the sign determined this 5 sigma. Or
yeah. At least for the lower terms. I mean, of course, you can always construct more, right? You can construct some complicated formula where that is not true anymore. And you would not see it in the data because it's wherever it is. Right?
The other question, is it known for cross-section or for form factors separately?
It's known for the cross-section. Okay. But even if this just complicates the picture, but even if you take that simple picture, right? You want to control all your systematics to half a per mil. That is challenging, right? Of course, what helps is that the relative measurement, right? You compare forward angles to slightly less forward angles. So any slope is important, not the absolute value, but still you have to control that slope.
Well, you already set it to 1 the first term, right? So you normalize
the
distribution.
Yes. Yeah. So you need 2 measurements, and the relative change in these 2 measurements, the error in the relative error in these 2 measurements, you have to control to half a per mil. Right? If in this simple picture, of course, it's more complicated if you have more data points and all of this, right? But that gives you like a benchmark number how well you have to control your effects, including radiative corrections. And I think that's hard. So what I think about too is JLAB and PRED. We have actually a talk coming up about that. It has some nice advantages. The calorimeter measurement, so energy resolution is worse than compared to, for example, Mainz, but you only get 1 setting or 2 settings for 2 energies, so it's all in one. And you can calibrate with Muller. The good thing there was they had the fit function figured out before they took the data. And Ashot's talk is later today on all that. But to show a little bit of what came out of that, I mean, the aim was to measure these points, like low cube points to get the radius. But if you compare the overlap, you see this difference between the Mainz data and the PRED data. And I'm not sure what to make of that. You can shift the Mainz data a little bit around and stuff like this. If you compare it to an old fit, so that's everything, the purple line, that's actually pre-Mainz, so that's the old data. They like this normal fall, and PRED has this almost constant compared to the standard data. So there's a discrepancy there, which is not only the photon radius puzzle, it's a different puzzle, and we have to figure that out. And that worries me, because what does this actually mean about what we know about form factors at higher Q square, right? Is this true? I mean, it's probably not coming up. That's an artifact of the fit. But if it's true that it stays up here, or does it go down at some point? Does it hit the points here, or stays it up there? Right? And why is it not the same? I mean, it's a very similar measurement sometimes, right? So that worries me. And especially if PRED is fully right, I think it really puts a question mark on all the data we had before, because that somehow has to like connect. And I don't see how it connects right now. We don't know where that difference comes from. Is it theory? Is it an experiment? What is it? I will not speculate a lot on the experimental part, but we can think about what is different between these two experiments. Right? Certainly the momentum resolution, so that's the tail shape, which comes to the radiative corrections. And the kinematics, right? PRAD is very, very forward, high energies, very forward, while the older measurements, including MINES, is lower energies at large angles. So the radiative corrections are different. You test different parts, different kinematics, different regimes of the calculations. Mia actually has something on Wednesday where we at least tested the shape, the tail shape in MINES, and we will talk about that. But it doesn't have to be the tail, right? It could be just the overall factor. If there's something not correct there, I could see this produced. There's actually some arguments why the high Q square of MINES is not completely off. Talk about the Olympus yields and a new measurement for MINES, which is very importantly not analyzed by me. So there's no bias, at least not from me. So Olympus yields, this was originally a measurement for the two-photon exchange. I will show that as the second part. But we managed to extract yields for electron-proton and for positron-proton scattering. And if you sum them up, you can cancel two-photon exchange, right? Instead of measuring it, you cancel it. And we get something which is at least where the MINES data is, right, up to 1, in agreement with the old fit. We do not see this structure here, which is in the old data, in the older data, if you have a flexible fit. If you don't have a flexible fit, it's not very, it doesn't force the fit to go through there. Just your chi-squares if it works. And that's preliminary. So the thesis is actually written by Julian. He analyzed this. This should come out soon. Then the newer data in MINES, where we repeated the MINES experiment at higher energies. And that fits very well to the old extractions and actually just fits with everything we had before. Speaking of this large Q, that's the other thing I'm worried about with the form factors. We had this puzzle, or this other puzzle, about the form factor ratio, right? If you divide GE over GM, you can access this with unpolarized measurements, but you can also access this with polarized measurements. And you can see here the unpolarized measurements, they essentially give you the scaling, right? So it's the ratio is constant, while polarization had this downward linear trend. With the newer fits, this is actually, with the MINES fit at least, this is actually a little bit resolved here. And it's the new fit from Euler, this is actually pushed down a little bit. But then it's an open sum. And we believe that this is the photon exchange which drives this. So people tried to measure this. And we had 3 experiments, Lab 3, one at JLAB and Olympus. And if you look at them and compare them with some of the theoretical models, if you look at the fit quality, they don't fit that well. This is actually not a model, that's the prediction from the difference, from our fit. So it seems to, at least Web 3 agrees with this, but the theoretical calculations do not. So we do not have a handle on that. Class didn't compare it with us. When that paper came out, they essentially declared victory and said, oh, we have everything in control. Our chi-squares is good, we understand it. I think this was a little bit premature. Again, our model is better, but well, not calculation, phenomenological model. So again, I would take from that the theory does not completely capture it. And Olympus shows the same thing. So this is the normal plot. I also have one where the points are a little bit more concentrated, where again, our prediction is good and Peter's model is different. I put Peter here on the stand because I think that's what we all believe we would measure. I think that's the model which should work best in that range. And it doesn't quite somehow. It's a different way to show this. So this is from all the experiments, the measured 2 gamma minus the predicted 2 gamma. So the points should scatter around 0. You see there's a systematic shift compared to Peter. And we don't have that from the prediction. But what worries me here is these 3 points. Because suddenly we overpredict the effect. So we need more strengths than we measured to explain these 3 points for 2-fold motion. So it could be that that discrepancy is actually not completely resolved by 2-photon exchange. Right? So the measured 2-photon exchange is not big enough to explain what we need. This might change with updated data. This is marginal. You see the error bars. But that worries me. What's going on there? Is it 2-photon exchange? Is 2-photon exchange the whole story? And certainly we do not have a complete theoretical handle on it, which is a problem because at these higher Q squares, we also haven't measured it. And we're pushing higher and higher, and we want to do that. And I mean, we don't know what's going on.
Can we shout in the session or are we keeping questions until the end?
Whatever you like.
So I'm more worried about the previous plot that showed a much bigger discrepancy with Peter's model in the small Q-squared region. Okay.
This one, yeah.
Then it's the standard is to use it to extrapolate at high Q-squared and apply it to JLAB data. And if it is not vetted at low Q-squared, there's a big concern whether that extrapolation is valid.
For the GPT model, it has exactly this figure going down and then crossing here. So like squared. This behavior is just like there.
Once I ask that question, if you take really that point out from that data, then the result is consistent with what structure.
That is.
That has to worry you.
Yeah, the error bars are huge. I would not interpret too much into that, but the ones with the small error bars.
I mean, this picture is.
Well, small error bars are even worse than consistency of no effective or wrong.
Well, if you look at it this way, right, there's the statistical on top of that, the systematical on top of that, right? But I think we calculated a couple of sigma significance that it's not 1. Right? And there's actually no good reason that it's 1, right? This is the hard part of 2-photon exchange. Why should be hard part of 2-photon exchange be zero, right? Yeah. There's no reason that the cutoff the theory arbitrarily put in between soft and hard just makes the hard part disappear. Right? It's not a good reason. So I don't expect this to be 1.
The soft part has been applied to theory as well as the data.
Yeah.
So it's in comparison between data and theory, we would still see that discrepancy independent of what's soft over there.
No.
Theory and
No.
data would move at simultaneously, depending on that cutoff.
Yes. Okay. Yeah, that's true. If you compare theory curve, but the 1 would change, right? Yeah. What does 1 mean? 1 means there's no effect, right? And it still means that the change you picked produces no effect, right? Yeah. Right. So somehow we don't really have a full handle on this, and it's getting to really percent precisions and below where it's hard, right? Yeah.
The prediction was Peter's theory, right?
So the blue line is Peter. Yeah.
So what the next slide that you're showing, difference between measured and predicted.
Yes, that's Peter's. Yeah, that's Peter's. Yeah, that's Peter.
And sorry, may I throw another one in? There was another plot that Axel had shown, I think it was in our paper, showing the higher order effects and how that influences the whole data set. And that was at the 1% shift level.
No, I think that was more. That was 6%.
No, the overall scale was 6%, but between the 1 plus delta and the exponentiation version.
Oh yeah, which variant of the radial fraction?
Yeah. That kind of encompasses all of the higher order effects. Right? It's like the two most extreme versions, and that margin was moving the data set up or down by about 1%.
Yeah, I think that's a little bit of a simplification, but yeah.
And I think this workshop should also kind of address how to deal with the higher order.
Yeah.
And why should this be the two extreme cases?
That might not be accurate. That might not be accurate what I said. Well, two examples.
Yeah.
Calculations here, yes, n or n plus delta.
So I think this one is the n plus delta one. And in this plot I had both, right?
Yeah, sure, but on this plot, the next plot.
I mean, if you look at this one, the dotted line is n only. Delta kicks in, doesn't really kick in until 2 squared. So it's almost all just the nucleon intermediate. And it's very difficult. I mean, the Feshbach correction is a little bit below 1, at very low 2 squared.
Yeah.
If you're going to come up with another mechanism that's two photon exchange, maybe some background text, some tie-in background or something which is not in simple mode. I don't have an explanation for why it would go below 1. I think it's very hard to envision. Unless somebody has some sort of background calculation.
There's certainly the possibility that it's not below 1, but you have to shift it by essentially 2 times the systematics.
Okay.
And then you have to shift these up and this point up less.
Well, everybody agrees that there's no correction at 2 squared 2. Or
Yeah. So it's doable, I think, with Olympus alone. But I think if you go back,
how certain are you about the systematics? Is it reasonable to shift everything up by 1 standard deviation?
Well, I think 1 standard deviation doesn't do it, right? So 1 standard deviation is this. So if you shift it up by 1 standard deviation, you are still just below in that range. So you have to shift it up another 1.
Okay, let's shift it by 2 standard deviations. But it's not, as I said, it's not going to be the same at every.
It's so the systematics here are global,
yes.
Right? So you really, you shift up all of them at the same time.
But
so
the
it's
point on the far right, you can't shift up. That makes no sense.
Yes, and that's where the problem is, right? If you shift them all up, I expect the other one to shift too, from how it worked out. And so there must be an effect which shifts the other one up and this one down. And it's a little bit, right? And you see it also, you don't see it only in Olympus. If you look at the class data sees the same thing, right? It's less strong there, but it's certainly there. Who doesn't see is at Webb, but Webb doesn't know where that point is. So they move that point to 1, right? If you move that point down, that point comes down. So Webb unfortunately doesn't help there.
So if I ask, how sure are you that you have the right Q-square?
That's essentially geometry, right? So you know the scattering angle.
Yeah, but what about the radiation? If you have collinear radiation, which is not a small effect, if Q-square changes.
Sure, but that's in the simulation, right? So you have
And what accuracy is it in the simulation?
That's the question: is how good is the radiative corrections in the simulation?
Exactly.
That's there is the generator we used for Olympus is based on the Mainz generator, and that is tested how the tail shape is actually predicted, and that works quite well, at least for the Mainz energies where we could test it. It certainly has a problem if you go really, really deep into the tail, like where the initial state radiation rise starts again. But these electrons, we would, I mean, we reject in Olympus because we have a momentum measurement. So we have a peak. So we are close to the elastic peak to some degree. So I don't think, I would be very surprised if Q-square changes could explain this. Yeah.
You bend the relation. Collinear radiation is not an issue because it's not detected in the same.
Because all photons are solved and they're close to peak. They're often close to peak.
If you can what collinear photons?
There are no factors.
Collinear photons are not bent by magnets.
Yeah,
you cannot forbid the electron to meet the collinear photon that you put a magnet or not. It's directly to the
energy of electron is measured, and energy of electron is not far from electron.
Yeah.
So the question is how much you can change this further. There are so many effects of the picture.
And you can only make the Q-square smaller, right? So it could be that these points are actually moving over there. But suddenly, I mean, maybe they move from here to here, right? There's just not, I mean, I think our Q-square control is good enough to say that. It's also a ratio. So if there's an effect, right, we cancel that to some degree. I mean, we really just put it somewhere else. It's not like, oh, we do the simulation wrong and get a completely different cross-section out. Because we do that error twice in the ratio, that cancels. It's really just where we put this point. There's no other lever. Right. But yeah, that's so maybe I'm at 45 minutes now. But but I mean, this is what worries me. Okay, so the third thing which worries me, we're really going to higher energies, right? And better statistics. So at JLAB and EIC, the new experiments are all, or many of them are not statistics limited anymore. They are systematics limited. So really all the systematics which go into that, some experimental ones, but also the theoretical ones are what limit our knowledge. And with higher energies, some things get easier, but some things get more problematic, right? You have more intermediate states you can produce, right? If you're above pion thresholds, there could be pions. If you're above, I don't know, proton thresholds, you could have protons. If you are even higher, whatever you have, right? And we need really to generate or to study this. We don't need, we need more than just like a theoretical calculations. We need to have generators which can actually produce this and see how the detector responses to that, right? And they need to be fast, right? We cannot throw millions of events which are all at a small cross section and hope that we hit the one good cross section, right? And then move this through Gaussian 4 because that will not converge in our lifetime. Right? We have to know how to generate these events. All right, so that's what I'm worrying about. Some better news. So a couple of people, Ethan, Axel, Craig McRae, and me, started to work on an open cross-section form factor database. And that should not be only a collection of the cross-sections and form factors we could just copy from the papers. We want to have it as a database which is annotated, what radiative corrections have been applied. So that you can take that data set and say, I want all of the data with these radiative corrections so that it's mapped to that, and it calculates the kinematics for that, and you can take it and take a fit. That was in our big paper, a large effort to get all of that in, and know that many people replicate that work, and I think that's pointless. And we really should make it in a way that we can update this and have a consistent data set with all of the metadata there. This also forces people to actually publish this metadata correctly so that there are no papers where you have, okay, this is the result, but what radiative corrections did you actually use, right? because that changes over time. We know more. And it's hard to go back and update this if you don't know these informations, right? It's even hard for some of the papers, right? Normally they had a hard cutoff at an energy, and they'd never say what that energy is, right? So is it 2% or is it a fixed energy or whatever? You have to guess that. And we should somehow make that a little bit more future-proof. So we hope that we get that going. We started programming it. It's more of a like side project, so it doesn't have that much time. But it would be very good if we could some help, especially from theoreticians who can like provide the code for their radiative corrections, so we can plug that in and don't have to, or at least cross-check that the results are correct, and stuff like that. All right. Yeah, this workshop, Ethan said most of it. Just a reminder for the people who are now new here. We want to take a cool picture. I would say maybe Wednesday after lunch or just before lunch outside. That's always a nice thing. Lunch will be organized by ECT Star. We have the 2 dinners, right, today and on Thursday. The other days, you are left to your own devices, but feel free to self-organize, right? There are a lot of nice restaurants, and it's always nice to go there as a group. We don't have to be the big group, but it's nice to discuss over dinner. All right, that's all from me.